All right, so you guys are taking these by hand, these notes. We're talking about random distribution and expectation today. So please make sure that you're taking smart notes. Also kind of color coded it a little bit. Red are like the notes. Anything in black are just like examples that we'll talk about together in class, and blue are the examples that I would suggest that you would write down, okay? But as always, make sure that you guys get down your goal. As today, you guys are going to learn how to determine the possible values for a variable that a variable can take, as well as assigning probability to those respective variables. Okay, so there are many variables out there in the world, and a lot of these variables depend on chance. Okay, some of these could be like the number of players on a football team who could potentially score points in a future match or something like that. The time it will take you to the time it takes you to travel to school and things like that. Okay, you know, there's different variables out there that, you know, can account to probability. Okay. However, because we cannot predict the exact value of a variable of chance, or that a variable of chance can take when it is measured, we can often determine a possible values that a variable can take. And we can assign to each possible value a probability of that particular instance occurring, okay? Now, when you do that, you're basically dealing with some type of random variable, okay? Now, a random variable uses numbers to describe the different possible outcomes, which could result from a random experiment, okay? A random variable uses numbers to describe the possible outcomes, which could result from a random experiment. Majority of the time, what you're going to see is that those different outcomes are represented by a capital letter, such as X. X is the most common, but there are other variables that can be used, such as Y and Z, okay? These types of variables can either be discrete or they can be continuous. Both of those words should be familiar to you guys when we went over statistics back last year. Remember, discrete is something that can be counted, such as the number of players on a football team, versus continuous, which is something that can be measured, such as height or weight, okay? A discrete random variable, X, has a set of distinct possible values, okay? Whereas a continuous random variable, X, can take any values within some interval on a number line. Hence, again, something that can be counted, or a specific number when it comes to discrete, or a range, an interval of values, and that would represent continuous, okay? Are those two words starting to pop up? Are they starting to sound familiar?
Yes.
Yes.
And you did in biology too? Yeah. So you've definitely seen it a few times, okay? So remember, discrete, something that can be counted, continuous, something that can be measured, okay? So again, just to harp on that. The number of defective light bulbs in a purchase of 50, that would be an example of a discrete random variable. So X, our random variable, okay, could take on the values of 0, 1, 2, 3, 4, 5, 6, all the way up to 50, okay? But basically what X is gonna represent is X is gonna represent the number of defective light bulbs within that purchase of 50. So you can either have 0, which means that there are no defective light bulbs, or you can have up to 50 for all 50 being defective. Or the number of pins a bowler can knock down in a frame. Okay, so X could be the values from 0 to 10, okay? Because they can either knock down no pins, 0 pins, which would represent a gutter ball, or all 10 pins for a strike, okay? Again, the things that can be counted, you can count that, discrete. The heights of men, that's an example of continuous, okay, which can lie in an interval between 50 centimeters to 250 centimeters. Again, X representing that continuous random variable to represent that range of values. Or the volume of water in a tank. Again, that's continuous because that's something that can be measured. anywhere between 0 meters cubed, which would represent an empty container, up to 100 meters cubed, which would probably represent a full container, okay? Just making sure that you can see how that random variable of X, it can be represented either discretely or continuously. For applications and interpretation specifically, you will only be responsible for knowing discrete random variables. So again, things that can be counted, not measured. Now, that's not saying that you should not be able to recognize the difference between discrete and continuous, because as you know, with statistics, we did like normal distribution curves and things like that, that did deal with continuous data as well. So, but for specifically discrete random variables or random variables and binomial distribution, which we'll deal with on Thursday, it's going to be only discrete type of values. So let's check out this example here. I'll give you guys a second to write it down. So a supermarket has 3 checkouts, A, B, and C. A government inspector checks the weighing scales for accuracy at each checkout. The random variable X is the number of accurate weighing scales at the supermarket. We want to list the possible outcomes and the corresponding values of X. And then we want to identify which value or values of X correspond to there being 1 accurate scale or at least 1 accurate scale, okay? So at this supermarket, we have 3 checkouts, A, B, and C, okay? And this person's coming in to check to make sure that the weighing scales are accurate for each checkout, okay? So if you think about it, this person could come in and they could check, you know, scale A, scale B, and scale C. And what could be something that could happen when this person checks them out? What's something that could happen?
They're inaccurate.
All of them are inaccurate, right? All of them would not work, okay? So if all of them don't work, then the probability distribution to represent that particular situation, or the value that will be associated with that random variable X would be what? If none of them are accurate, X is supposed to represent the number of accurate weighing scales, then the number would be what?
0.
It would be 0 because none of them are accurate. But what's another option that could happen? They could all work. All 3, he can go and check, and A, B, and C, they all work. Then what would the number that would be assigned to the random variable X be?
3.
It would be 3 because all 3 of them are working. Because remember, X represents the number of accurate weighing scales. Are those the only 2 options we can have?
No.
Okay, then give me another one. What could happen?
2 of them could work and the other could be broken.
Right, so like A and B could work, but then C could be broken. Or A and C could work, but B could be broken. Or
B could be an A, or fixed and A could be broken.
B and C are accurate, but A could be broken. Any one of these situations that could happen, what's the value for the random variable X?
That's 2.
2 for every single one of them, okay? Are these my only outcomes?
No.
Okay, well, what are some other outcomes that could happen?
Only one of them could work.
Yeah.
Only one of them could work, all right? Such as, let's see, I'm out of space here. Well, if I extend this a little bit, there we go. So then A could be the only one that works, right? But then B and C could be broken. Or B could be the only one that works and A and C is broken. Or A and B are broken and C is the only one that could work. If that was the case, then what would be the random variable X? What would be the value associated with the random variable?
1.
Be 1. These are all the different outcomes that could happen if that inspector goes and checks this out for these weighing scales. All of them could work, all of them could not work. 2 could work, 1 of them could work. These are all the different outcomes and the corresponding values to represent our random variable X, which is the number of accurate weighing scales. But now that we have this table, we can actually see what value or values of X correspond to there being 1 accurate scale. Well, to represent 1 accurate scale, that means that X would have to equal 1. Okay, if X is equal to 1, then that lets us know that's either going to be A is going to be accurate, B is going to be accurate, or C is going to be accurate. At least 1 accurate scale. At least 1 means that there could be 1 that's accurate, or 2 that's accurate, or all 3 that's accurate, because it says at least 1 accurate scale. So the value or values of X that represent there being at least 1 accurate scale would be 1, 2, and 3. This example here is showing how these could be represented using just the symbols versus the words. So if you were asked, let's say that it told you that X was equal to 1, and it didn't even write this out or any of this out, this will let you know that, okay, they're wanting, the outcome of only 1 of them being accurate. Like, it doesn't have to be in words, they can represent it using symbols as well. That's what this example was supposed to show.
Can you give again how you did at least 1 accurate scale?
At least 1, remember, at least 1 means that 1 is the lowest number that could be accurate, but we could have up to 3 accurate scales. So that's why for B double I, X could either equal 1 or 2 or 3, because it said at least 1.
Okay.
So it's that range. Now, how do we use this? Well, for any random variable, there is a corresponding probability distribution that helps describe the probability of the variable, or that the variable will take a particular value. And that is represented by what you see at the bottom. P, parenthesis, that's a capital X equals a lowercase x. Okay, so that there is a difference there. You got a capital X and you got a lowercase x. Okay. So this is where that basic knowledge of probability kind of comes into play, okay? So the capital P represents probability, okay? Probability. The capital X represents our particular random variable. And then our lowercase x actually represents that like numerical value that's associated with our random variable, okay? So anytime you see this type of notation, it's basically asking you, okay, what's the probability that X will equal a particular value, or there could also be like a greater than value or less than value instead of the equal sign value, okay? Couple of things that you need to remember about probability, especially when it comes to a random variable, is that for one, all of your probabilities are going to lie in between 0 and 1 inclusively, okay? So all of your probabilities for all of your different random variables, they're either going to be equal to 0, in between 0 and 1, or equal to 1. okay? So that P sub I is basically saying, so your probability of 1 happening, probability of 2 happening, all the way up to however many you have. The second one says, this symbol, what does this symbol mean?
The sum of.
It's sigma notation, it represents the sum of. So it's saying the sum of from 1 all the way up to n of all of your probabilities. So that's saying all of your probabilities, when you add them up, should equal 1. And then for the third one, it's basically saying that all of your different probabilities that represent each one of your random variables, they describe a probability distribution. They describe a probability distribution. So all of your probabilities should lie between 0 and 1. When you take all the possible probabilities of a particular random variable, they should all add up to equal 1. And once you have all of them present, all of your probabilities together represent a probability distribution. So for that last example that was talking about a person coming in, checking out these scales, right? A person coming in, checking out these scales. Okay, these were all of our different outcomes. These were all the different ways that we could represent our random variable X. Okay. We have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 total outcomes that could happen when this person comes in to check out these different scales. Okay. I am going to erase this part, okay? Because we already written this down, right, from before. I'm just trying to get myself a little bit more space. Okay, so if this guy comes in, the probability, and you see this is basically saying the probability that none of the weight scales are accurate, right? Essentially what you do is you look, okay, well, the number of times that 0 shows up is 1 time out of how many? Out of 8. So the probability that this government official is going to come in and find out that all the scales are not accurate is going to be a 1 out of 8 chance, okay? The probability that exactly one of them works, how many times does 1 show up? 3 times. 3 out of 8. Let's keep going. What's the probability that 2 of them will be accurate? 3 out of 8. And the probability that all 3 will be accurate? 1 out of 8. If you look, every single one of these probabilities that represent each of the random variables is in between 0 and 1. That was that first situation when it came down to your rules there. The second one says that the sum of all your probabilities should add up to equal 1. Well, 1/8 plus 3/8 plus 3/8 plus 1/8. They all have the same denominator, so I just add the numerators. 1 plus 3 plus 3 plus 1. Does that give me 8? 8 out of 8, that's equal to 1. Together, this represents a probability distribution, okay? And so from there, you could be asked, what's the probability that the inspector will, find 2 of them that are accurate? Well, you'll be able to say 3 out of 8 because you've created this probability, or you create this distribution essentially table here, okay? These distributions can be represented as either a table or as a graph. What I did in that last example that I was writing in blue, I essentially wrote out every single probability for you. But more than likely, you're going to see it represented as a table to represent your probability distributions or as a graph, okay? The table is the most common, essentially puts all of your different outcomes. So 0, 1, and 2, and then their respective probabilities of 1/4, 2/4, and 1/4, okay? But again, all of your probabilities, all of these add up to equal 1. All the probabilities are in between 0 and 1. So that makes this a probability distribution. So just to continue to make sure to harp on this, to make sure that everybody understands. So for example, suppose X is the number of heads obtained when 2 coins are tossed. So the random variable X is the number of heads that are obtained when 2 coins are tossed. The possible values for X are what? You flip 2 coins, and X is supposed to represent the number of heads that you get when 2 coins are tossed. What are the possible values of X?
0, 1, and 2.
0, 1, and 2. Because I can flip both coins and they both land on tails. So that means no heads. Or I can flip both coins, one of them's heads, one of them's tails. Or I can flip both coins and they both be heads. If that is the case, then the corresponding probabilities would be what? What's the probability that I will have 0 heads if I flip 2 coins? Not 1/3.
0 out of 4.
Not 0 out of 4, because if you're saying 0 out of 4, you're basically saying that it can never occur, but it can occur.
So 1/4.
It'll be 1/4. Because remember, I can either have tails, 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 heads, or I could have what? Heads, tails, or heads, heads. So the probability of getting 0 would be 1 out of 4, but the probability of getting 1 head would be what?
2 out of 4.
2 out of 4, which reduces down to be
1/2.
1/2. And then of course, to get both of them to be heads, it's going to be 1 out of 4. Always make sure you guys reduce your fractions. Always make sure you reduce your fractions. Some of y'all didn't on your midterm. Please make sure you reduce your fractions. It is possible to have a uniform, discrete, random variable. Okay, that happens when all the outcomes of X have the same probability of occurring. Okay, that can happen like, when you roll a die, a fair die, the probability of you landing on any of the numbers is 1 out of 6, right? So that you can have a uniform, discrete, random variable. However, if you were to roll 2 dice, the sum would not be a uniform, discrete, random variable, okay? Then moving forward, something else that you could be asked, remember this probability went with statistics, so I want to make sure you haven't forgotten certain things such as mode and median. You could be asked to find the mode of a discrete probability distribution. Remember, mode is the one that shows up the most. In a probability distribution, it would be the value with the highest probability. The mode of a discrete probability distribution is the value that has the highest probability. The median of the distribution will be the one that corresponds to the 50th percentile in ascending order. So in other words, wherever 50% lies, that 50 percentile, that data value represents your median. Okay, that data value represents your median. So if I take this probability distribution table that represented the number of heads that can happen when you flip 2 coins, what would be the mode of this distribution? It'd be what? It'll be 1, because it's the one that has the highest probability, and 1/2 is bigger than 1/4. The median would be the data value where the 50th percentile lies. Well, clearly it would not be 0 because that's like your first 25%. At the end of 1, you're at 75% because you got 25% and 50%, that makes 75%. So the 50th percentile lies right here. So your median would also be 1 as well. Does everybody understand that?
Yes.
All right, get down this example. A magazine recorded the number of magazines purchased in 1 week by its customers. 23% purchased 1 magazine, 38% purchased 2, 21 purchased 3, 13% purchased 4, and 5% purchased 5. We're going to let X be the number of magazines sold to a randomly selected customer. We want to state the possible values of X. Well, remember, it says we're going to let X be the number of magazines sold. So what possible values could X be? Don't all go at once. The X is going to be the number of magazines sold. When I go back and I reread that paragraph, it said magazines recorded the number of magazines purchased in 1 week. Probably go back and redo that. 23% purchased 1 magazine, 38% purchased 2, 21% purchased 3, 13% purchased 4, 5% purchased 5. And if X is the number of magazines sold,
Oh, yeah.
X is equal to what?
Would it be,
One
would
through
it be
5.
1, 2, 3, 4, 5?
Yes, 1, 2, 3, 4, 5, because that's the number of magazines they sold. Okay. Now it says construct a probability table for X. That was the table that I showed you a few slides back, where it had X, a lowercase x at the top, and the probability of capital X equals lowercase x at the bottom. Now remember, the small x, the little x, represents all of the different possible values that the capital X can represent. So that's going to be 1, 2, 3, 4, and 5. What does the capital P represent? Probability. Remember, probability cannot align between 0 and 1 if it's in the fraction form. But in this case, we have percentages. So we're going to need to do what to those percentages? Determine what? I think I know what you mean. I don't think you're explaining it well. I can't put 23% in here because this is not percentages. These are probabilities. So how would I?
0.21.
Yep, I will have 21 to represent 3 magazines purchased. What would I do for 1 magazine purchased?
0.23.
Oh, and then for 2?
0.38.
For 4?
0.13.
And for 5?
0.05.
Okay. Now remember, this is a probability distribution. All of those pink numbers should what?
Add up
Equal
to
100.
Either equal 100% if I had the percentages in there, but add up to equal 1, which they do. 23, 38, 21, 13, and 5, they all add up to equal 1. So this is a probability distribution. Okay. Now we have to graph the probability distribution. Well, essentially, we just have to take those values and put them on a graph. Okay. Going back just to refresh your memory, these are the 2 different graphs that you could do to represent a probability distribution. As you can see, your X values are on the X-axis and your probability is on your Y-axis. So that's what you want to do for this example. You want to have an X-axis, a Y-axis, of course, positive here. Your X is representing 1, 2, 3, 4, and 5. And then your y's representing the probabilities that go along with it. Since my largest probability is 0.38, I'm only going to go up to about 0.4. And then I'll 0.1, 0.2, 0.3, 0.4. And I make nice bar graphs. Not a histogram. They should not connect. Remember the difference between bar graphs and histograms. Histograms connect. These should not. So 0.23, it's a little bit bigger than 23. 0.38. 0.21. 0.13. And 0.05. So let's find the mode and the median. Remember, mode is the one that has the highest probability. So what's the mode here? How many magazines?
2.
2 magazines, because it had the largest probability, which was 0.38. And now my median. Remember, median corresponds to the 50th percentile. So if I start at the lowest one, which was 1, I only have 23%, 0.23. When I go to 2, I'm going to add those together. What's 23 plus 38?
61.
So 0.61 is once I've gotten through all of the two magazines. So my 50th percentile actually lies within magazine 2. So my median is 2 magazines as well. Questions? Now, this doesn't always have to revolve around like a word problem where you have to create your own table and things like that. You could be given a probability mass function, which is essentially like an equation, like an actual function, okay? But a probability mass function is the set of possible values of a variable, and the range is the set of values in the probability distribution. So instead of giving you, some big drawn out description about a guy selling magazines or somebody flipping a coin, they could give you a function with corresponding values, and you can create your own probability distribution, okay? All you need to do to create that probability distribution is actually take each one of those X values and plug them in to the respective function. Okay. So I would take 1, plug it into the function. That'll give me 1 squared plus 1 over 34. What's 1 squared plus 1?
2.
So that'd be 2 over 34. Of course, reduce your fractions. That's going to be 1 over 17. By taking each of the X values and plugging it in to that function that's given to us, we can create our own probability distribution table and answer whatever questions we would need to based off of that. So that'd be 2 squared plus 1 over 34, 3 squared plus 1 over 34, 4 squared plus 1 over 34. You guys go ahead and find the rest of those different probabilities, please. What's the probability of 2?
5 over 34.
And for 3?
5 over 17.
It'll be a 10 over 34, which reduces down to 5 over 17. And the last one?
17 over 34.
17 over 34. That does reduce down to be
1/2.
1/2. Okay. Now it is asking you to show that this that probability, or to show that it's a valid probability mass function. Again, all these probabilities should add up to equal what?
1.
1. So if I keep it with the same denominators to make it just a little bit easier on myself. 2 plus 5 is 7. 7 plus 10 is 17. 17 plus 17 is 34, and 34 out of 34 is indeed equaling 1. So yes, this is a probability mass function. Okay, so it can work with actual situations like the magazines, or you could be given a function, but it still rolls the same way. Okay, still rolls the same way. So if I wanted to, I too could put this in a probability distribution table with its respective probabilities. Okay, it works both ways. Along with probability, just like it was back when we did basic probability with these different types of distributions, there is this idea, this concept of expectation, okay? Just to review expectation from the past, we use probability to predict the number of times we expect an event to occur, okay? So back in the day, if I'm a 75% free throw shooter in basketball and I take 100 free throws, how many am I expected to make?
100.
If I'm a 75% free throw shooter,
Oh, 75.
I'm only gonna make 75 out of those 100, right? And you get that by multiplying your number by your probability. Okay, that's what it was before we got to these distributions. For random variables, your expected value is the sum of all the X values multiplied to their probabilities, added up together, okay? That's how you find expected value for a probability distribution, okay? With these random variables. Instead of just multiplying the X value by the probability and getting like 4 different ones, you add them all up together. And that's how you get your expected value. Capital E of capital X is the mean of the probability distribution of X. So not only does it represent expected value, but it can also represent the mean. And it is denoted sometimes with the Greek letter mu, okay? It is represented sometimes with the Greek letter mu. So if you're asked to find the mean of a probability distribution, they're asking you to take all the X values, multiply them to their probabilities, and add them up together. If they ask you for the expected value or capital E of capital X, again, you take the X value, take its probability, multiply them together, then add all of them up together. That's how you get your expected value. So let's take that magazine example, okay? The one where the person, they had a 23% purchase 1 magazine, 38% purchase 2 magazines, and so on and so forth, okay? We're asked to find the expected number of magazines bought by each customer. The expected number of magazines bought by each customer. Well, remember, expected number. That's when we take each of our X values and multiply them to their respective probabilities and add them up. That's when we take each of our X values, multiply them by their respective probabilities, every single one, and we add them up. That's how we find the expected number of magazines bought by each customer. That's also how we find the mean number of magazines bought in a week. That's also how we find mu. It could be represented several different ways, but we take each of the X values and we multiply them to their respective probabilities and add them up. So my answer here is going to be 2.39. I'm not going to round that to say, oh, well, that's about 2 magazines, because the question didn't ask me to round in any particular way. This is expected number. So what does this mean? What does this represent? That on average, 2.39 magazines are purchased. Remember, anytime you explain something or justify what it means, you do it in context of the problem. So on average, 2.39 magazines are purchased in 1 week, because that was the description that was given to us previously with the original problem, okay? And then you can even add per customer, because I know I left that part off because I was trying to save some space, but it was basically by, each person will buy that many magazines or whatever. So far, a lot of things to take away, okay? We got expected number, also known as the mean. You take your x values, multiply them to the probabilities. This was a probability distribution because all the probabilities added up to equal 1, okay? What if I gave you, I'm gonna add this in, what if I gave you a probability distribution table? No description, no nothing, okay? And I gave you this. And I asked you to find the mode. I asked you to find the median. And I asked you to find the mean. In order to do any one of these three things, what are you going to need to know?
A.
I got to know A. And using what you know about a probability distribution, how can I find A?
It has to add up to 1. So 2/5 is 4/10, and 4/10 plus 1/10 is 5/10. So A is 5/10.
Very good. So you have to add all of them up together and set it equal to 1. It needs to equal 1. So you're right, that's 5/10. So that means that A has got to equal 5/10. Okay, or you could say 1/2. It actually might be more helpful, if anything. Oops, maybe to put them as that, so in that way, you might be able to see a little bit easier. So what's the mode? Which one shows up the most?
2.
Very good. Where's the median?
2.
Very good. And then to find the mean, what would I have to do?
Add all of them and divide by 3.
No. That's what we did. That's how you remember, mean is also the same thing as expected value. How do we do it?
Multiply the first and second row and then add them up.
Yes, we got to multiply the first and second row and add them up. The reason why we can't do it the other way is because they're not equally weighted, right? This isn't a uniform probability distribution. If it was uniform, then we could do, add them up and divide by however many. But because they each have their own different probability, we have to take each x value and multiply it by its respective probability, then add. So when we do that, what do we get? So this one,
Or 17/10.
it'll be 17/10 or 1.7. Remember, we do not, even if these x values represented like people or something, we do not round mean unless the problem tells us to round to like the nearest whole number or something like that. Okay, very good. I just want to make sure, because when that shows up in your homework, I don't want you to be like, oh, you didn't do an example like this. Well, I thought I harped on the fact that all the probabilities have to add up to equal 1, and that mean is the same thing as expected value. Okay, cool deal. One more concept, and then we'll sum it up and we'll be done for the day. In gambling, yes, IB talks about gambling. The expected gain of a player from each game is the expected return or payout from the game, less the amount it costs to play. Which makes sense, right? When you go and you put a bet on something, right? And if you win, your expected return is what you get after you subtract however much it costs for you to play the game, all right, or how much you put in for the bet. A game is said to be fair if the expected gain is 0, or if capital E of capital X is equal to 0. So if you're ever asked, and the question is this game fair? Well, find out what that means. Find out what the expected value should be. If it equals 0, it's a fair game and you can take your chances there, okay? So let's look at an example that talks about this because it still deals with like probability distribution. And then we'll be done for the day. In a game of chance, a player spins a square spinner labeled 1, 2, 3, 4. The player wins an amount of money according to the table alongside. The first thing we have to do is we have to find the expected return for one spin of the spinner. So this person is going up to play this game where he has the spinner that has these different numbers on it with these different respective winnings. Now, what's the probability that's associated with each one of these sections of the spinner?
1/4.
It's going to be 1/4, okay? Because it doesn't say that one particular section takes up more real estate than the other. So we can assume that each section is equally spaced, okay? And so then to find expected return, we want to take our X values and multiply them by the probabilities. And since it's asking us for the return, it's essentially asking us for how much money we could potentially win. So our X values here that we want to use to determine the expected return are our winnings, So to find our expected return, we're going to take each one of our winnings and multiply them by their respective probabilities. Each one of our winnings multiplied by each one of our probabilities. So what is 1 times 1/4 plus 2 times 1/4 plus 5 times 1/4 plus 8 times 1/4? Four. So our expected return, if we play this game, is $4. Our expected return, if we play this game, is $4. Now, it's asking us to find our expected gain of a player if it costs $5 to play the game. Well, remember, expected gain from the previous slide is the return, the expected return from the game less the amount it costs to play the game. So our expected return was $4. So to find our expected gain, I would take that return and then subtract it from how much it cost for me to play the game, which was $5. What's $4 minus $5?
Oh, $1.
Careful.
Oh, sorry, -1.
It's going to be -$1. Because if we put in $5 to play the game and our respective return is $4, we actually are losing money to play the game. So with that being said, would you recommend playing this game?
No.
No, do not play this game, okay? It is not, if anything, it's not fair, okay? Because as we can see, the gain is in the negative. In order for a game to be fair, which, I probably would say, take your chances, is if your expected gain equaled 0. Because it does not equal 0, it's not a fair game. You're more likely to lose money than actually win money by playing this game. And that's how you can determine if a game is fair or not as well. Okay, the expected gain should equal 0. All right. And that's random distribution along with probability distribution. You're taking these different discrete variables, you're assigning probabilities to them based off of information that you're given or information that you can find. And you're determining different things based off of them. Okay, a few things just to make sure that everybody does have this down. For a game to be fair, expected value should equal 0, or your expected gain should be 0. So that's after you take out however much it costs for you to play the respective game. Also, that probability or how to find expectation, you just take all your X values and multiply them by your probabilities and add them up. Don't forget about the sigma notation. Probability distributions, all the probabilities should add up to equal 1. All your probabilities should be in between 0 and 1 in order for it to be a probability distribution. And of course, mode and median, mode being the highest probability, median being the 50%. Okay, but that is random variable and probability distributions and expectations.